All right, let's get right into it. We're going to crack two of the most fundamental ideas in all of chemistry, the Bohr model for seeing an atom and the mole for counting them. Nail these two, and you're well on your way.
So here's our game plan. We'll start super small, visualizing one atom. Then we'll learn its language. After that, we're going to scale way up, learning how chemists actually count and react trillions of them at a time. It's all about going from the micro to the macro.
First up, the Bohr model. Now think of this as your go-to mental picture for what an atom looks like. It's simple, it's clean, and it's a fantastic place to start building your understanding of atomic structure. So here's the big idea. Right in the middle, you've got this dense core called the nucleus. It's packed with protons and neutrons. And zipping around that nucleus, kind of like planets orbiting the sun, are the electrons. But, and this is key, they aren't just flying around randomly. They're stuck on specific paths called energy shells. Okay, this next word is huge for your exams. Seriously, lock this one in your brain. The word is quantized. All it means is that electrons have to exist at specific energy levels. They can be on level 1 or level 2, but they can't be in between. Their energy comes in distinct, separate packages. This is probably the most important rule of the Bohr model.
And this ladder analogy is the perfect way to remember what quantized means. Think about climbing a ladder. You can stand on a rung, right? You can be on rung 1 or rung 2. But can you float in midair between the rungs? No way. It's the exact same idea for electrons and their energy levels. It's a fantastic mental shortcut.
Okay, so we've got a picture of the atom. Now, how do we write it down on paper? How do we speak its language? That's where atomic notation comes in. It's the shorthand chemists use to describe exactly what's inside any atom.
Now, this might look a little technical, but it's actually super straightforward. X is just the letter for the element from the periodic table, like Mg for magnesium. A, the number on top, is the nucleon number. That's the total count of protons plus neutrons in the nucleus. And Z, down below, is the easy one. It's the atomic number, which is simply the number of protons.
Let's put this into practice with a real example, this magnesium ion. Okay, look at the bottom number, Z. It's 12. Boom, that means 12 protons. Easy. Now look at the top number, A. It's 24. How do we get the neutrons? You just subtract. 24 minus 12 gives us 12 neutrons. Finally, the electrons. See that 2+ charge? That tells you it has lost 2 negative electrons. So instead of 12, it has 12 minus 2, which is 10. See? Just a few simple steps.
All right, we've totally nailed the single atom. But in a lab, we're not working with just one. We're working with numbers so big they're hard to even imagine. So how on earth do chemists count that high? The answer is the mole.
Just take a second to look at this number. It's huge. 602 billion trillion. That's Avogadro's constant. It is a ridiculously massive number, and it represents the number of particles, atoms, molecules, whatever, in just 1 mole of something. So what the heck is a mole? Honestly, don't overthink it. It's just a counting number. Kind of like how a dozen means 12, a mole just means, well, that giant number we just saw. It's the magic bridge that connects the invisible world of single atoms to the amounts we can actually see and weigh in a lab.
Okay, before we dive into the math, let's meet the key players. You're going to see these 4 terms everywhere. You've got mass, which we measure in grams, the mole itself, the molar mass, which is just the mass of 1 full mole, and then relative atomic mass, which we'll dig into in a sec.
Now for the really cool part. Let's see how we use these terms to jump between the two worlds, to convert from a mass you can weigh on a scale to the number of moles that it actually contains.
This is a super common trip-up, so let's clear it up right now. Atomic mass unit, or AMU, is for one single atom. It's microscopic. Molar mass, on the other hand, is for a whole mole of atoms, that giant number. It's macroscopic. The number itself, like 12 for carbon, stays the same, but the scale and the units are completely different.
And that finally explains why relative atomic mass, or AR, has no units. You ever wonder about that? It's because it's not a direct measurement, it's a comparison. It's really asking, how heavy is this atom compared to a tiny slice of a carbon-12 atom? And since it's a ratio, the units just cancel each other out. Pretty neat, huh?
Awesome. We can count atoms now. So let's actually make something. The best way to think about a chemical reaction is that it's just a recipe. And the balanced equation? That's your list of ingredients and their exact proportions.
Take a look here. The big numbers out front tell you the recipe.
You need exactly 2 moles of sodium hydroxide to react with every 1 mole of sulfuric acid. That 2-to-1 ratio is the golden rule for this reaction. And it has a fancy name, the stoichiometric ratio.
But what happens if your measurements aren't perfect? What if you just dump in too much of one ingredient? Well, the reaction is going to stop as soon as one of them runs out completely, right? The one that gets used up first, we call that the limiting reactant. And the one you have some leftover of, that's the excess reactant. Finding the limiting one is the most important step.
And here it is, your 4-step game plan for solving any of these reaction problems. Just follow these steps in this order every single time, and you'll nail it. Balance the equation, convert everything to moles, find which one runs out first, and then use that one to calculate your answer. Simple.
We're in the home stretch now. For our last topic, we're going to look at what happens when the perfect world of our on-paper calculations meets the messy reality of the lab. This is all about theory versus practice. These terms are pretty intuitive. Theoretical yield is your perfect world number. It's what the math says you should get if everything goes 100% perfectly. Actual yield is, well, what you actually end up with, the amount you measure on the scale at the end of your experiment. Spoiler alert, they're almost never the same. So, how do we grade ourselves on how well the experiment went? We use this formula for percentage yield. Think of it like a grade for your reaction. It compares what you actually got to what you theoretically could have gotten. It just gives you a simple score that tells you how efficient you really were.
And one final, quick term for you, mole fraction. All this is a way of describing the composition of a mixture. You just take the moles of the chemical you care about and divide it by the total moles of everything in the mix. It just tells you its fraction of the whole pie.
And that brings everything full circle. Just think about it for a second. We started this whole thing by just trying to get a simple picture of one single atom. And we ended it by being able to predict what happens when trillions and trillions of them crash into each other in a reaction. How amazing is that? That leap from understanding the one to predicting the many is the real magic of chemistry.